Okay. All right, so today we are going to start the third lecture set. Okay. And the third lecture set in this class is devoted to the study of probability and the basics of interpretation, calculation, and the study of the fundamental or foundational relationships that exist across events that can occur simultaneously or at a different time. So the purpose of this lecture set is to give you an introduction to how you would calculate and interpret a probability, how you would relate or study different events that can occur independently or separately from one another and calculate their probabilities, and give you insight into some of the different counting rules or enumeration formula that we can use in this class, one of which we will see again after this lecture set. But for the most part, this is the only lecture set where we will study probability in any great detail. And again, it's meant to be a foundational set in that it's giving you insight into the interpretation of a probability and what it means to actually have a value, well, what it means to actually have a probability and utilize this going forward. Okay, so the interpretation or definition of a probability is something we will continually come back to throughout the class. So from this point forward, we will be using probability in some way, either to make a decision or to make a decision or to explain the likelihood of observing a particular event. And again, this is the intro to that particular concept. All right, so the first thing, what is a probability? I mean, very briefly, like a probability is simply a fraction, or it's a value that takes the number of ways some event that you're interested in can occur and divides by all of the possible things that can happen in the particular experiment or situation that you are involved in. So we let capital N designate all of the different outcomes that can occur inside of an experiment. And we're using experiment here not necessarily to mean like, you know, you're inside of a lab and you're doing some kind of following some sort of procedure. The experiment can just mean, you know, like you're rolling a die, or you are, you know, trying to determine the outcome of any different, well, event. You know, like it could be you're trying to determine the probability that the Oilers will win, I don't know, 40 games this year or something like this. Like that would still count as an experiment in this context. So we let capital N designate all of the different things that can occur within the experiment that you are interested in. We let capital E represent the event that is of interest to us. So capital E can be anything that we would like to calculate the probability of observing. And then we let little f designate all of the different ways that this event can occur. So we write P, open bracket, capital E, close bracket, to mean the probability of observing event E. And we say that the probability of observing event E is equal to little f over n. So all the ways the event can occur divided by all of the possible outcomes within the experiment of interest. We're going to talk about each component of this calculation separately. For example, the next thing that we will do is discuss what is called the sample space. And the sample space is essentially just a list of all of the different outcomes that can occur within an experiment. So the sample space is a list of size capital N that shows us all of the different things that can happen within a particular experiment. Okay. And it's also worth pointing out that every probability calculation boils down to what's given on slide 3. So to little f over capital N. In any situation, if we are able to recognize how many ways a particular event can occur and also count all of the possible things that can happen in a particular experiment, we can compute the fundamental probability, or the probability for equally likely outcomes via equation 1. Okay, so here are some important properties of a probability, and these are things that are fairly simplistic, but they are valuable because you can always use these to make sure, well, you can always use the first point in particular to make sure that you have done your calculations correctly. A probability is a value that exists between 0 and 1 inclusive. So a probability can never be negative, and a probability can never exceed 1. So anytime we are working with, or we are trying to compute a probability, if we're not working on the percentage scale, our answer should always be between 0 and 1, and it can include 0 or 1. If the probability is equal to 0, we say that that is the impossible event. So this is an event that would never occur. If the probability is equal to 1, we say it's a certain event. So this is an event that will always occur. Okay. So 0 indicates not going to happen. 1 indicates always going to happen. And then you have a scale between 0 and 1 that indicates basically how likely it is or is not to occur. Right? It follows that because every experiment has capital N possible outcomes, the certain event is going to have capital N different ways of occurring, and the impossible event would have 0 ways of occurring. So again, momentarily, we'll start talking about the sample space in a little bit, but we'll see that in that list, if the event that is interested is not shown, this would be an impossible event. And if the event that is of interest is the only event shown, this would be a certain event. Okay, so here's some very basic probability questions just to get an idea of working with the formula. An experiment has 25 possible outcomes. All are equally likely. An event can occur in 14 ways. What is the probability this event occurs? All right, so here we have little f is equal to 14. We have capital N is equal to 25. It follows that the probability of observing event E is little f over capital N is 14 over 25, which is equal to 0.56. Okay. In question 2, it asks, which of the following is not a valid probability and why? So in this case, the answer would be 3.5. 3.5 is greater than 1, therefore not valid. Right? So all probabilities must be between 0 and 1 inclusive. So a probability of 3.5 would be not valid. So this would not be a probability that makes any sense. Okay. An ordinary deck of playing cards has 52 cards that are split evenly across 4 suits and 2 colors. Can I skip? No. Okay. So there are 4 suits: diamonds, hearts, spades, and clubs. If one of these cards is selected at random, calculate the following. Okay, so just in case you aren't as familiar with card structure or deck structure, 52 total cards. Okay. There are 13 hearts, 13 diamonds, 13 spades, and 13 clubs. Okay. So the hearts and the diamonds are also red cards. which gives you a total of 26 red cards. And the spades and the clubs are black cards, which gives you a total of 26 black cards. So in a standard deck of cards, we would, in an experiment like this, we would always let capital N be equal to 52, because every time you draw one card out of the deck, you have 52 different possible cards that you can observe. Among those 52 cards, you have 26 red cards, 26 black cards, 13 hearts, 13 diamonds, 13 spades, 13 clubs. Okay, so in this question here, it asks, what is the probability of observing a spade? So we would have N is equal to 52, little f is equal to 13. The probability of observing a spade is going to be 13 over 52, which is equal to a quarter. Okay, similarly in part B, what is the probability of getting a red card? Okay, so again, N is equal to 52, F is equal to 26. The probability of observing a red card is going to be 26 over 52, which is 0.5. Okay, and then C, what is the probability of not getting a club? Okay, so in this case, N is 52. F is going to be 52 minus 13, because there are 13 clubs in the deck. Everything else would not be a club. So that gives us 39 different options that are not a club. So then probability not a club is going to be 39 over 52, which is 0.75. Any questions so far? All right. Suppose two fair coins are flipped simultaneously. Give the sample space for the experiment. What is the size of the sample space? What is the probability that two fair coins both show heads? What is the probability one of the two fair coins both show a tail? Okay, so here, our experiment is tossing two fair coins. All right, now in part A, we're being asked to give the sample space. So the sample space is a list of everything that can occur when you toss the two coins. Okay, so we have sample space lists. Some of these words are. Sample space lists everything that can happen when you toss two coins. Okay, so there's a lot of different ways you can write the sample space. I'll just write it like this. So I'm going to put coin 1 here, and I'm going to put coin 2 here. Now what I'm going to do is I'm going to write down what can occur on each coin. So for example, one of the possible things that can happen is that I get a head on coin 1 and a head on coin 2. I could also get a head on coin 1 and a tail on coin 2. Or I could get a tail on coin 1 and a head on coin 2. Or I can get a tail on both. Okay, so this is my sample space. The other way that I can write this is S, oh, sorry. S, so this here is sample space. S is equal to head, 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 tail, tail, head, tail, tail. Okay, and this would be the more formal notation for the sample space. So the fancy S, and then inside the curl brackets, you're listing all of the possible outcomes. Okay, either way, you can see here in part A, our sample space is composed of 4 different events. So the size of the sample space, which is question B, part B, is capital N equals 4. Okay, and then we have in part C, what is the probability that the 2 fair coins both show a head? Okay, so here we're going to have capital E is equal to, so the event is equal to HH. All right, so we're going to have little f equals 1, capital N equals 4. And then we would say the probability of E, which is the probability of observing 2 heads, is equal to little f over n, which is 1 over 4, which is 0.25. So you can see again, everything is just boiling back down to that same fundamental probability. So the probability of observing event E is equal to little f over capital N. In this particular question, we had to write out our sample space first, but then once we had our sample space written out, we've just come back to that same fundamental formula. In D, it asks, what is the probability one of the 2 fair coins shows a tail? 1 second, Raleigh. What is the probability one of the 2 fair coins shows a tail? Okay, so here we can write capital E is equal to, let's say, 1 tail. Okay. All right, so now we can see that there are 2 different ways that this can occur. We can either have head tail or we can have tail head from the sample space. So F is equal to 2, N is equal to 4, and then we would have the probability of E is equal to the probability of observing 1 tail, which is F over N, which is 2 over 4, which is 0.5. Okay, Raleigh, is there a difference between capital N and sample space? Capital N is the size of the sample space. The sample space is a list of all of the possible outcomes. So in part A, I have listed all of the outcomes. That would be the sample space. In part B, I have given the size of the sample space, which is capital N, and that's equal to 4. Does that make sense? Any other questions? Okay, suppose two fair six-sided die are rolled simultaneously. Give the sample space for the experiment. What is the size of the sample space? And then we have three different probability questions. All right, so this question is pretty much the same as the last question, except that we're dealing with a different experiment now. So in this case, instead of rolling two fair die, we are instead of flipping two fair coins, we are rolling two fair die. So this would be the situation when you play Monopoly or when you play a game like Settlers of Catan, any die rolling game where there's two die that are being involved, this would be the sample space that gives you all of the possible outcomes. Yeah, Catan is also my favorite game. We probably play, I would say I play Catan about 4 times a week with my family. And it gets very uncomfortable and very competitive. But it's a great game, despite the fact of the uncomfortable competitiveness. Yeah. That's awesome. When I was back in my day, when I was your age, I used to play that a lot with my roommates too. All right. Sample space. Okay, so this will inform your Catan decisions, though on Catan it actually tells you the probability of the outcomes. They have like numbers and little dots under the numbers, but this is going to follow the same, this is going to reveal the same conclusions. All right, so writing out the sample space for this event is going to be a little bit more tedious because there's more possibilities, but this is how I like to enumerate a sample space for die rolling questions. So I'm going to start by labeling die 1 here. And then I'm going to put die 2 here. Okay. And then I'm going to make a cross tab. All right. Now die 1, you can roll 1, 2, 3, 4, 5, or 6. Die 2, you can roll 1, 2, 3, 4, 5, or 6. Okay, now what we're going to do is we're just going to match the two outcomes up together, right? So here you can get 1, 1, 1, 2, 1, 3. I guess I should do this in the proper order if this is die 1. So you can have 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 2, 3, 2, 3, 3. Oh no. 4, 2, 5, 2, 6, 2, 2, 3, 3, 3, 4, 3, 5, 3, 6, 3. Okay, 2, 4, 2, 5, 2, 6. This makes more sense. 3, 4, 3, 5, 3, 6, 4, 4, 4, 5, 4, 6. 5, 4, 5, 5, 5, 6, and then 6, 4, 6, 5, 6, 6. All right. Okay, so everything inside the cross tab, these represent the different possible outcomes. So again, if we wanted to, we could do this in the formal way where we have capital S, curly bracket, and then we would start listing all the outcomes. Okay, so I'll just list a few for illustration purposes. Right, and then you would go 2, 1. Okay, and then you would continue to list them until you got up to near the end. So then we would have like 6, 5, 6, 6. Okay. Now in this case, when we count the size of the sample space, you can see that we have 36 different outcomes. So there's 36 different things that can happen when you roll 2 die at the same time. And those 36 different outcomes make up our sample space, okay? And the list of those outcomes is given in the cross tab, but we could also write it in the more formal way if we wanted to. Okay, now we can start to break this apart. So in part C, it says, what is the probability that both die show a 1? Okay, so here we can say the event is going to be 1, 1. So then we can write the probability of E is the probability of observing 1, 1, which is going to be F over N. We can see that there's only one way of getting a 1. So here we have little f is equal to n, and capital N again is 36. So this is going to be 1 over 36. And I need to, 1 second, Shelby. Where's my, there it is. I don't know what 1 over 36 is off the top of my head. Okay, so this is 0.027 repeating. Okay. So the bar here over the 7 just means repeating, like the 7 just goes on and on forever. So 0.0277777777777 forever. Forever and ever. Shelby B. Does it matter how we show then sample space on assignments? It doesn't matter to me. Some students would prefer a more formal notation so that they can standardize their lists across all questions. So if you want to have that standardization and that consistency, then the capital S notation would be the way to do it. This is also how we write it in the solutions, but that doesn't mean you would get it wrong if you did it as a crosstab, for example. In most cases, you're going to need to use some sort of tabular format like what I've shown here to figure out all the outcomes anyways. So you're probably going to have to go through the first step to get to the more formal notation. But as long as you have everything listed, it'll be accepted in terms of the assignment. Yeah, so sorry, then I went on to answer the second part of the question. So for those watching at home, the second part of the question is, can we do it like the chart if we prefer that, or does it have to be the actual notation? Yeah, so again, if you prefer the chart, that's fine. But if you prefer the notation, then that's also fine. Okay, part D says, what is the probability that exactly one of the die shows a 1? Okay, so we're looking for a situation here where we only have a 1 on one of the die. So we're not looking for the joint outcome in this case. That exactly one of the die shows a 1. Okay, so here we have, we'll call this 1. No, let's do it like this. We'll call it 1, 1. Okay, so exactly 1, 1. Actually, let's just use the word exactly because it makes it more clear. All right, so now what we're going to do is we can use our sample space to figure out which events are going to correspond. Okay, so I'm going to use the color green here to represent these values. So we're looking for a situation where we have exactly 1, 1. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So there's 10 different ways that we can get exactly 1, 1. Then we have capital N is equal to 36. So the probability of E, which is the probability exactly 1, 1 is going to be 10 over 36, which is going to be 5 over 18 and 5 over 18. Oh, that's kind of cool. Is 0.277. Well, actually, I don't need the second one. 0.27 repeating. Right. Okay, and then part E, what is the probability the two die show the same number? All right. So here we're going to have two die same, or like you could write a Venn is same number, however you want to express it. Okay, so I'll use the red here to mark this one. So you can see that we have 1, 2, 3, 4, 5, 6 different events that correspond to this particular, or 6 different ways of observing this event, which is both die being the same. So little f equals 6. N equals 36. The probability of E, which is the probability to die same, is 6 over 36, which is 1/6. What is a sixth again? Never compute in public. I don't think I would have got that anyways. 0.16 repeating. Any questions? All right. Okay, so, yeah, you can think about it. So sorry, Shelby, just to clarify, little f is essentially all the possibilities from the sample space that answer the question. Yeah, you can think about it like that. That would be a less formal interpretation because it's based on the fact there has to be a question to answer, but that is not incorrect in the context of what we are going to be doing. Good. All right, so we have just done 5 exercises that have all been devoted to sample space enumeration, so listing out the sample space and computing fundamental probabilities based on that sample space. Now what we're going to do is start to talk about different relationships that we can use to describe different events within the same sample space. So essentially the idea here is we can ask for probabilities of specific events using a particular statistical notation to mean a specific kind of event. So for example, the first relationship that we're going to discuss is the complement. And in our area, our field, like the probabilistic field or statistical field, the complement simply means the opposite of. So for example, in the previous question, we asked, what is the probability that every die gives the exact same number? We could ask, for example, what is the probability every die does not give the same number? Which would be similar to what is, or would be the same as, what is the probability of observing the complement of every die giving the same number? So the complement simply means opposite of. Now, to compute the complement is quite straightforward. Every sample space, all possible outcomes, or sorry, the probability of all possible outcomes across the entire sample space has to equal 1. So if we want to find the complement of a particular event, we would do 1 minus the probability of that event. And the complement can be designated as either E, or it can be designated using either the bar symbol or a little c in the superscript. So these two notations here these both mean complement, right? So just two different ways of saying the same thing. Whichever one you prefer is fine. There isn't one that's more right than the other. There's just multiple notation for complement. And in every case, when we want to compute the complement, we're simply going to find the event that's of interest and then do 1 minus that event. The other two events that we will discuss in this class are union and intersection. The union, or sorry, the intersection represents the space where two events occur at the same time. So they occur simultaneously. So in order to specify a union or an intersection, we have to have two different events within the same experiment. So in the context of the die rolling example, what we could do is let event A represent something that happens on die 1, and let event B represent something that happens on die 2. And then we can start to discuss unions and intersections between the events. So technically, in the previous illustration where we had the die rolling experiment, in that illustration, we were computing intersections of different events. So we were looking at simultaneous outcomes between die 1 and die 2, which we can think of as intersections. There are 3 different ways to write intersection. They are shown here. Okay. So we have A and B. So A and B at the same time. A cap B, which is the middle one. Okay, so this part, this little symbol here is the cap, or A and B with an ampersand. Again, it doesn't matter which notation you use, whichever one you're more comfortable with is fine. We typically just use A and B with the ampersand in this class. The cap notation is the more formal notation that you would start to see as you move on to higher level probability courses. We can write the probability of the intersection using our standard P notation. So you can see below I have P of A and B, P of A cap B, or P of A ampersand B. All of these mean the same thing, just the probability of the intersection. So when we don't have the probability symbol, we're asking for a list. When we have the probability symbol, we're asking for the probability. So those are two different things. So we can either list all of the outcomes, or we can give the probabilities of the outcomes. And I'll show some examples of that in a little bit. Okay, the other event that we will see quite often is the union. So again, starting from the point where we have two different events in the same sample space, the union represents the space where one of the two events can occur or they both occur. So the intersection is part of the union. The union is designated as A or B, or A cup B. Okay, so this is a cup union. And just like before, we can either list all of the elements that belong to the union, or we can give the probability of the union. And again, we'll go through some examples of what this means in a bit. But just to recap very briefly, we have fundamental probability and the sample space. And now what we're doing is we're saying within the sample space, you can have a direct event that's of interest to you, or you can have a complement, an intersection, or a union. So we're studying 3 different relationships among multiple events within the sample space. All right. When 2 events have no intersection, so when A and B has nothing inside its list, or the probability of A and B is equal to 0, we say that those events are mutually exclusive. Okay. So mutual exclusivity refers to 2 events that have no intersection. So anytime we are told that 2 events are mutually exclusive, it means the probability of their intersection is equal to 0. All right, so it's a definition in that sense. So this is just something you need to commit to memory. Okay. So an example of mutually exclusive events would be anytime you roll a single die. So if you roll just 1 die, it's impossible to observe 2 numbers at the same time. You can only ever observe 1 number each time you roll the die. So that means that any situation where you're trying to observe 2 numbers on 1 roll does not exist, and therefore those 2 situations are mutually exclusive. Okay, so we've explained those definitions verbally. I'm now going to explain those definitions via Venn diagrams. Okay, so a Venn diagram is a pretty simple illustration that can be used to represent different events within a sample space. So we consider the box to be the sample space for a particular event, okay? So the box here is going to be capital S. Within the box, we draw some shape. So most often we use, for example, a circle. All right, we're going to label the circle, I'll call the circle here capital E. So the circle represents all of the different possibilities within the sample space that refer to the event of interest. Okay, so the complements, so the probability of E bar is everything outside of the event of interest. Okay. So if the box is our sample space, the probability of observing the complements is basically the area, or is the area outside of the event of interest. So everything that is not included within the circle. Okay, so for the other 2 events that we talked about, we now need to consider 2 different outcomes. And I can use this same box. Okay, so the first one is going to be the intersection. Okay, so here we're going to let each circle represent event A and event B. The intersection refers to the part that overlaps. Okay, so the intersection of two events is the area that the two events share. The union is going to be what they share and each component separately. So the union represents everything across the space of the two events. So you can see that the intersection, again, is a subset of the union. When two events are mutually exclusive, they do not intersect. So this last diagram is an illustration of two mutually exclusive events because the probability of the intersection is equal to 0. Okay. So two events that are not intersecting, that do not overlap, are mutually exclusive. So they have no, or they have a 0 probability for the intersection. Okay, so these are the three main events that we're going to talk about in the next part of the lecture set. And the last definition, which is the definition of mutually exclusive, this is, again, something that we need to commit to memory. So mutually exclusive events never intersect. This is a definition. All right. Okay, so let's suppose a 6-sided die is rolled one time, and we have 4 different events within the space. So first, let's just really quickly list the sample space for this event so that we have it. Okay, so S for a single 6-sided die is just going to be the possible outcomes on that die. Right, so 1, 2, 3, 4, 5, 6. All right. Okay, it says event A is the event the die comes up even. Okay, so event A is going to be 2, 4, or 6, because those are the 3 even numbers that exist within the sample space. Event B is the event the die comes up 4 or more. 4, 5, 6. Event C is the event the die comes up at most 2. So this is going to be 1, 2. And event D is the event the die comes up 3. Okay, so this is going to be a 3. All right, now we're being asked to describe the outcomes that constitute the events. So what we're being asked to do here is not compute a probability. We're simply being asked to list the events that correspond to parts A, B, and C. So in part A, we have not A, which is the same thing as A bar, which is the same thing as AC. So we're just being asked for the complement of event A. Okay. Event A is the event of observing 2, 4, or 6. The sample space is comprised of 1, 2, 3, 4, 5, 6. Okay. So therefore, not A would be everything that is not 2, 4, or 6 in the sample space. So this is going to be 1, 3, 5. The second event is A and B. Okay, so the and means intersection. So we are looking for the components of A and the components of B that are the same. So we have 2, 4, 6, 4, 5, 6. So the components that are the same are going to be 4 and 6. So the intersection of 2, 4, 6 and 4, 5, 6 are 4 and 6. Okay, and then in the last one, we have B or C. So here we are looking to list everything that's in B, everything that's in C, and their intersection. So for B and C, we have event 4, 5, 6, and then we have events or outcomes 1 and 2. There's nothing that is the same here, there's nothing that is the same here. So the union is simply going to be everything that's in both. So we're going to have 1, 2, 4, 5, and 6. No, you only list the intersection once. Sorry, so the question was, if there was a number that is the same, would you list it twice? No, you would only list it one time. Okay, if we want to compute the probabilities of the intersection and the union, for intersection, we just need to know what parts are the same, and we can compute that probability using little f over capital N. For the union, we have special rules that we can use to compute that particular set of outcomes. Now, going back to the question that was just answered, do we list the elements that are the same twice? We do not. And as a result, when we compute the union of intersecting events, we actually have to subtract off the intersection so that we do not double count it. So if we want to compute the union of mutually exclusive events, that is very easy to do. We just add the individual probabilities together. So anytime we have events that are not intersecting and we want to know the probability of observing all those events, or the probability of observing one of those different events, we just add the individual probabilities together. That's equation 3. If we have events that are intersecting and we want to compute the union, our formula for computing the union of intersecting events changes every time we add a new event into the space. So most often we will be computing the union of intersecting events when there's only 2 events. So we'll be using equation 4. So equation 4 says, if we have event A and event B, and we want their union, and we know that they are intersecting, then the probability of the union is equal to the probability of A plus the probability of B minus the probability of A intersect B. If there are 3 events in the space, you can see via equation 5, the probability of the union becomes more complicated. The point is, anytime that we have multiple events within the space and we want the union, we have to know which events are intersecting and which events are not intersecting, because that influences how we compute the probability of the union, because we do not want to double count the intersection. So equations 4 and equations 5, they both assume that all events intersect with each other. But we can have situations where this isn't the case, and you have, for example, intersection between A and B, but no intersection between B and C, and you have to account for that.
Gary.
Okay. That scared me. All right, any questions? All right, so let's go through some different exercises that are related to computing the probabilities of the three events that we just talked about. So the first exercise is, suppose that A and B are mutually exclusive events where the probability of A is 0.25, the probability of B is 0.4, and we want to determine the probability of the union. Okay, so first things first, we are told that A and B are mutually exclusive events. Okay, so this means that the probability of A and B is equal to 0. Now we want to find the union. So since A and B is equal to 0, the probability of A or B is equal to the probability of A plus the probability of B, which is 0.25 plus 0.4, which is 0.65. Okay. So since we have mutually exclusive events, the union is simply the sum of the probabilities of each event. In part B, or number 2, sorry, it says, according to the Congressional Directory, the official directory of the US Congress, as of fall 2013, so this is very, very updated information, there were 11 senators under 50 years of age, 30 senators between 50 and 59, 37 between 60 and 69, 20 between 70 and 79, and 2 over 80. Okay, so we're going to let event A be the event the senator is under 50. Okay, so here, capital F is going to be 11. We'll write F of A is going to be 11 because we are told there's only 11 senators under 50. In B, it says the senator is in his or her 50s. Okay, so here we have F of B, which is going to be all senators in their 50s, of which we have 30, because we are told that 30 are between 50 and 59. C is the event the senator is in his or her 60s. Okay, so we are told there are 37 between 60 and 69. And F of S is the event the senator is under 70. So F of S under 70 would mean we actually have the sum of F of A plus F of B plus F of C, which is going to be 30 plus 37 is 67 plus 11 is 78. All right. Okay, so now we're being asked a few different questions. The first one is, what is the probability of C? Okay, so I think I can just fit this. I'll just do it on the next slide. Okay, so we want probability of C, which is the probability of the event the senator is in his or her 60s. So this is just going to be F of C over capital N. Okay, so P of, I'll do it on the next page. Okay, so P of C is going to be little fc over capital N. So we had 37 here. We need to work out capital N. Okay, so capital N is going to be the sum of all of the different senators that are within this directory. So we have 11 under 50, 30 between 50 and 59, 37 between 60 and 69, 20 between 70 and 79, and 2 over 80. So that should give us 100. Okay, so therefore P of C is going to be 37 over 100, which is just 0.37. Okay, in part B, it asks, what is the probability of S? Okay. So the probability of S is actually F of A plus F of B plus F of C divided by capital N. Okay, so this is actually an illustration of a union because S represents the union of A, B, and C. So here we have F of A plus F of B plus F of C, which we worked out to be 78. So I believe that was 11 plus 30 plus 37 divided by 100, which is 0.78. Okay. And then in part C, it says express S in terms of A, B, and C. Okay, so S is actually the union of A, B, and C. So S in terms of A, B, or C would be S is equal to A or B or C. And you can see that since A, B, and C are mutually exclusive, we're able to just add their individual probabilities together to get the union, which is what we did in part B. Any questions? S is the, okay, so the question is, S is the union of A, B, and C because they are all under 70. That is correct. So A are the people that are less than 50, B are the people in the 50s, C are the people in the 60s. Everyone under 70 would be all three of those collections together. Okay, so we're going to return to a die rolling example, and we are now going to designate two events that are taken from each die. So I'm just going to go back and grab the my little die rolling table from slide 7 so that we can use that here. So I'm going to copy and paste this. Okay, so this is our sample space here. Okay, so we have A is the event a 6 is rolled, and B is an event a 1 is rolled. Okay. So in part A, we have what is the probability of A bar? Okay, so A is the event that a 6 is rolled. Okay, so the probability of A bar is equal to 1 minus the probability of A. So this is going to be 1 minus little f over capital N. Okay, so this is going to be 1 minus something over 36. All right, so let's let A be marked in red here. Okay, so A is the event that a 6 is rolled. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so there's 11 different ways that we can observe a 6. So the probability of A is going to be 11 over 36. So therefore, the probability of A bar is going to be 1 minus 11 over 36, which is 25 over 36, which is equal to 0.694. Kareem, why 1 minus? Because we are looking for the complement. So we want the probability of A bar. The probability of A bar is 1 minus the probability of A. That's the definition of a complement. Okay. In part B, it says, what is the probability of A or B? Okay. Okay, so A is the event a 6 is rolled. B is the event a 1 is rolled. So you can see from the sample space that there are two different occasions where 1 and 6 occur at the same time. So A and B in this situation are intersecting events. They can happen simultaneously. So we can observe 6, 1, or we can observe 1, 6. All right, so this is going to be the probability of A plus the probability of B minus the probability of A and B. All right, so let's take a look at this here. So we'll let blue be A, we'll let green be B, and I'll let this cream color be A and B. Okay, so A is the event a 6 is rolled. Oh, I guess I should just leave that as red because we already did this one. Okay. Okay, so A is the event a 6 is rolled. So we know that this is going to be 11 over 36. B is the event that a 1 is rolled. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the probability of B is also 11 over 36. The intersection are the two outcomes that are in agreement between A and B. So we can see that here we have an intersection and here we have an intersection. So the probability of observing the intersection is then 2 over 36. So then we have 22, 11 plus 11 is 22 minus 2. So that's 20 over 36. Oh yeah, A or B. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, 20 over 36, which is 0.55 repeating. Okay, and then the last part is asking what is the probability of the intersection? Okay, so we actually worked this out above. This is 2 over 36, which is 1/18, which is 0.05 repeating. Sweet coffee. All right. Contingency tables next. 912. Damn it. Okay, any questions about what we've done so far? Are we marked on simplifying our fractions? No, you're not marked on simplifying your fractions, but it's a good skill. Any other questions? Are all of the probability rules in terms of union? No, the complement is not, the intersection is not. The union includes the intersection if the events are not mutually exclusive. So those would be different rules. Okay, kind of at a awkward time right now because this is a different unit and I need more than 5 minutes to do it. Okay, I think just for the sake of continuity, I'll just stop here for today. There's still 5 minutes left, so if can you go to slide 15? Yeah. Is there, sorry, Kareem, is there a question or do you just need to see it?
Yeah, I was just wondering if we calculated it.
No, it asked to, the question was express S in terms of A, B, and C. So this is the expression of S in terms of A, B, and C.
Oh, so there's no numbers involved.
No.
Okay, thanks.
Yeah, so I'm going to stop here for today with the material. There's still 5 minutes left, so I'll hang around if you guys have questions. A reminder that assignment 1 is due tonight at end of the day. All of the assignment parts A and B are to be submitted via CrowdMark. Assignment 2 is due in 2 weeks. Thursday, we will not have class because we are observing I'm sorry, I forget the exact title of the day, but Thursday we will not, Truth and Reconciliation Day. So we'll observe that. So there will be no lecture material or class on Thursday. So I'll see you guys next Tuesday for new material. I have office hours today, but they are going to start at 2 o'clock and go to 3:30 rather than from 1 to 2:30. And I'll send a reminder about that. That's all of the announcements that I can think of. So again, I'll hang around if anyone has any assignment questions, and otherwise I will talk to you guys. Do we have to attend Truth and Reconciliation? What do you mean? Do you have to attend it?